Welcome to the course Excelling with Mathematical Modeling. In today's lecture, we will be learning about the phase plane analysis. So, to start with, what is a phase plane? Consider the differential equation dx dt equal to ax plus by dy dt equal to cx plus dy. So, on the right hand side, as you can see, the terms are all linear. So, the idea is even if you have nonlinear terms, you linearize the system and then write it in this particular form. If I write them in the matrix form, I will be getting ddt of x and y, which is equal to a, b, c and d into xy. And clearly 0, 0 is the equilibrium point here. So, you must be wondering why we are doing all the analysis with 0, 0 only. If it is not a 0, 0, you can obviously change the origin to 0, 0 and they can do all the analysis. So, hence 0, 0 is always taken here, and also in this particular case you can see that 0, 0 satisfies this differential equation. So, now if I want to solve this and plot the graph, I can do it like this, that I can plot it. So, this is my t, this is my x t and y t. So, if I plot the graph, say it will start with some initial condition and it will show some dynamics. It will start with some initial condition and it can show some dynamics and go to the equilibrium point. Not in this case, because it must go to 0, 0, because that is the equilibrium point. I just took a random diagram. But the idea is that if you now want to plot against x t and y t, then what will you get? So, you think the solution to this system as the points in this plane x y, and the equilibrium solution will correspond now to this origin, and this x y plane is called the phase plane. So, basically you have this system of autonomous differential equation, you solve it, you get a solution, then this is say your x t, this is say your y t, and this is your independent variable t. But now you want the solution in terms of x and y. So, this is your x axis, this is your y axis, you want to plot, this is x, this is y, this is x y, this is x y, and you will get a figure somewhere. So, you want to see what kind of dynamics you get in this x y plane, and this x y plane is called the phase plane. So, you put one value of t, a particular value, and you sketch a particular solution. So, you have started with some initial condition here and you got a curve. That is called the trajectory. The trajectory of the solution. So, if you want what is a phase portrait, this is just the geometric representation of orbits of a dynamical system. In the phase plane. So, basically what it shows the trajectories of the system. So, you take one initial condition and you get one path, that is one trajectory. You take another initial condition, you get another path, this is another trajectory. You start from here, you get another, you start from here, you get another, and together all this will be known as a phase portrait. So, you need to remember what is a phase plane here, that is the plane on which you get the dynamics, that is called the phase plane. And for a single value of t or for a particular value of t, the solution which you get is called the trajectory of the solution. And for many initial conditions, that means many values of t's, you will get a system of trajectories which will ultimately give you a phase portrait, from where you can understand how your system is behaving. Let us now classify them. So, this is phase plane diagrams, which means phase portrait of linear systems. So, after you linearize them, you put the equation in the form dx dt as some lambda 1 x plus lambda 2 y and lambda 3 x plus lambda 4 y as an autonomous linear system, which has been put in this matrix form. Clearly, 0 0 is your equilibrium point, because it satisfies the right hand side, and if this determinant is not equal to 0, because this determinant means determinant A, which is equal to determinant lambda 1, lambda 2, lambda 3, lambda 4, which is lambda 1, lambda 4 minus lambda 2, lambda 3. If this is not equal to 0, then you have a unique steady state 0 0, because it becomes a homogeneous solution, homogeneous system, and the solution can be visualized as trajectory moving in the x plane and can be sketched, and those are called the phase portraits, exactly the one which I explained before. So, basically what you will do, you will get equations like this. You will find the equilibrium point, in most cases it will be 0 0, and then you just see where this determinant is not equal to 0, and then you plot this solution and you see what kind of dynamics you get in the xy plane, which are known as phase portraits. Now, to explain or understand this better, I take a simplified system of the form dx dt equal to lambda 1 x and dy dt equal to lambda 4 x. So, just in this previous equation, I put lambda 2 equal to 0 and I put lambda 3 equal to 0. So, lambda 1 x and lambda 4 y. 0 0 is the unique equilibrium point. It has been put in the matrix form. Then I find the eigenvalues of this matrix V. So, if you find the eigenvalues of this matrix V, you get the roots lambda 1 and lambda 4. So, these are the eigenvalues of this matrix V. Now, depending on the signs of the eigenvalues, whether it is positive, whether it is negative, whether it is positive, negative, whether it is complex, we are going to classify the solutions. So, the first thing is you solve and you get the solution to be like this with some initial condition or initial values x 0 and y 0. Now, if both this x lambda 1 and lambda 4, both these eigenvalues are negative, then what happens? Then you get here that e to the power minus lambda 1 t and e to the power minus lambda 4 t. So, as your time becomes large, so this trajectory will approach 0 0 and it will converge to the equilibrium solution 0 0 no matter what the initial condition is. So, as the time increases, you can see that e to the power minus lambda 1 t will go towards 0, same with here, and your x y will approach the point 0 0, which is the equilibrium point here. And hence, this steady state or this equilibrium point is called a stable node. So, you have to remember that you have been given a linear system, you find the eigenvalues, and if both the eigenvalues are real and negative, what you get is called a stable node. And this is how it looks like. When you will draw this diagram, so all you have to do is you take this is where it converges, in this case it is 0 0. So, you take one point here, 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 and all of them will converge to this particular point 0 0. The arrow is important, that is, it is moving towards 0 0, and this is a stable node. In this plot, you can see these are the vectors which can be plotted with the help of any software, and it is reaching the point 0 0. Now, let us see what happens if both of them are positive. So, obviously, if both of them are positive, then you have e to the power lambda 1 t and e to the power lambda 4 t. So, if both of them are positive, this will diverge from the equilibrium point 0 0, irrespective of whatever the initial condition is, and then your steady state is called an unstable node. This is the figure of the unstable node. So, it is exactly what you will do is you draw a node, you take one point in each quadrant. This line can be like anything, okay. It can be any curve. However, in this particular case, because it is an unstable node, the arrow will move away from the origin. So, the arrows are very important. This is unstable node. Now, let us take the case when one of them is positive and one of them is negative. So, then what happens? So, in this particular case, it is x t is equal to x 0 e to the power lambda 1 t and y t equal to y 0 equal to e to the power lambda 4 t. So, lambda 1 is less than 0 and lambda 4 is positive. Suppose I put a negative sign here. So, what happens? So, as t increases, your x t decreases, but your y t increases exponentially. So, this one tends to go to 0, this one becomes infinite. And all the solutions in this case will first approach this 0 0 for some time, but when they come close to it, they will move away from the steady state irrespective of whatever the initial condition is, and in this particular case, this steady state will be called a saddle point. So, in this case, what happens is that one of them is positive and one of the root is negative. So, due to the negativity, one solution will approach the origin, due to positivity, the one solution will move away from the origin. So, the dynamics says that after reaching close to this 0 0, it will just come out of the system and moves away. If you want to look into the dynamics, the phase portrait, so this is the phase portrait of a saddle. Now, how to draw this? This is very important. So, first thing is you draw this and then you draw two lines. So, first you draw this axis and then you draw these two lines. First is, in one line you just take the arrow inside and in one you take the arrow outside. So, inside means in that particular case the solution is moving in because of the negativity of one of the eigenvalue, and moving out is because of the positivity of the other eigenvalue. The rest of the solution will be like this. So, this is coming from this side and moving like this. So, coming from this side and moving like this. So, you put an arrow like this. Coming from this side and moving like this, put an arrow like this. Here also you put an arrow like this. Here also put an arrow like this. In the similar way, you just follow the path of these arrows and you just draw the figure. Like this. So, this becomes a saddle point. Let me draw this one more time. So, first is you draw the axis and you draw two straight lines passing through the origin, and then you just take one line where the arrow will move towards the origin, and another line where the arrow will move away from the origin. So, once you get these 4 arrows, you just see from this side it is moving to this side. So, arrow is like this. Similarly, here also from this side it is moving this side. So, arrow is like this. From this side to this side, arrow is like this, and from this side to this side, the arrow is like this. So, the figure of the saddle point. Let us move to case 4. So, now you have complex eigenvalue, and since it is a quadratic equation, we know that the values will be complex conjugates, and your dynamics will depend on this value of A. So, your solution is in this form, and suppose A is less than 0. So, if A is less than 0, both these eigenvalues will have negative real part. So, if it is a negative real part, then obviously this will decay, because as t becomes large, this will decay, and all these trajectories will spiral towards 0, 0, irrespective of the initial condition, and it is called either a stable spiral or a stable focus. If I want to find this solution, this will look somewhat like this, that it will start from somewhere and then it is some sort of damped oscillation like this. The oscillations are due to the presence of sine and cosine, and the damping is because this is negative and it slowly decays out. So, the trajectories which you get, or the phase portrait, looks like this. This is a stable focus. If you just want to draw them, you just take and round and round and round. So, the thing which you have to remember is that this point will never enters this 0, 0. It will just spiral round and round about this 0, 0. So, this is one point. I can take another point here. I can do like this. I can take another point here. I can do like this, and I get what is called a stable spiral. And as usual, the arrow is important. You are moving towards the origin. You are moving towards the origin. It's moving towards the origin, towards the origin. So, this will be a stable focus or a stable spiral. And when your A is positive, obviously the eigenvalue have a real positive part. In this case, e to the power at grows exponentially, and the trajectory will spiral away from your 0 0 irrespective of whatever the initial condition may be, and it is called unstable spiral or unstable focus. So, to draw this again, you draw the spiral and I will just arrow is outside, it is moving out. You can draw one more. So, start it from here, so it moves out, moves out. So, this is your unstable spiral or unstable focus. Now, what happens when your A is equal to 0? So, when A equal to 0, your eigenvalue becomes purely imaginary. So, in that case, is all trajectories will form a closed orbit like this, and the solution is periodic, because you will have only the sine and the cosine functions, and your solution will look like this, just a periodic solution. So, this is your t and this is your x t or y t. So, if you want to draw this, it is just a concentric circles, which is steady state will be called a center. So, you just draw some concentric circles and mark the arrow in one direction. So, this is called a center. To sum up, I put it in the tabular form. So, you have the system, a linear system, you find the eigenvalues and then you see whether it is real or imaginary. If it is real, whether the signs are negative. If it is negative, then it is called node and it is asymptotically stable. If both of them are positive, it is again called node, but it is unstable. Now, if they are opposite, one of them is positive, one of them is negative, it is called a saddle point and it is still unstable. If the roots are real and equal, in that case, if it is less than 0, it is node and it is asymptotically stable. If it is greater than 0, again it is node, but it is unstable. And when you get an imaginary root, then you check for the real part of the root. If it is less than 0, it is called a stable spiral and it is asymptotically stable. If it is greater than 0, it is again a spiral, but unstable. If it is equal to 0, it is center, it is stable, but not asymptotically stable. So, if you remember this chart, I think your job is done, and if the equilibrium point is not stable, it is then unstable. Let us take some examples now. Say we start with dx dt equal to minus x plus 4y, dy dt equal to minus x minus y cube. So, I find the, so I have taken non-linear, not the linear one. So, the matrix, so if I put this is as some f, this is as some g, this is fx, fy, gx, gy, we have already done this, and you will find these values as minus 1, 4, minus 1, minus 3y square at the point 0 0, because clearly 0 0 satisfies this equation and 0 0 is the equilibrium point. So, at 0 0 this value becomes minus 1 4 minus 1 0. So, I need to find the eigenvalues. So, A minus lambda I equal to 0, which implies minus 1 minus lambda, 4 minus 1 minus lambda equal to 0, lambda into lambda plus 1 plus 4 equal to 0. So, lambda square plus lambda plus 4 equal to 0. So, lambda is minus 1 plus minus 1 minus 4ac divided by 2a. So, minus 1 by 2 plus minus root 3I by 2. So, I have a complex root with a negative real part, and hence it is going to be a stable focus. So, you have a complex root with negative real part implies the equilibrium point 0, 0 is a stable spiral or stable focus, and the phase portrait is, you take like this, and since it is stable, you just put the arrows in like this. So, this is a stable focus. Let us take another example. So, this time let us take other equilibrium point which will be other than the origin. So, x minus 2y and dy dt is equal to y 2 minus x minus y. So, the equilibrium points this I leave it to you. I have already calculated that. So, this will be 0 0, then it is 0 2, it is 3 0 and it is 1 1. So, these are the 4 equilibrium points. You can easily check, you put this equal to 0 and solve them, and you will get these values. So, the next thing is I will calculate A. So, f x y is equal to 3x minus x square minus 2xy, gxy is 2y minus xy minus y square. So, del f del x, so 3 minus 2x minus 2y, del f del y minus 2x, del f del x minus y, and this is del g del y, so 2 minus x minus 2y. So, this is at the point x star y star, where your x star y star is these points. So, let us start with 0 0. So, if I put it, I will get 3 0 0 2, and clearly the eigenvalues are 2 and 3. So, they are real and positive, and hence it is unstable node. If you want the phase portrait or phase plane diagram, you choose 4 initial points. This is your origin. You just bring the curve here, and it is unstable, so it is moving out. So, that is the important part. You have to remember the arrows. So, this is your unstable node. In the similar manner, you can check for the other equilibrium points. The only thing you have to note here is when you are, say, checking for this 1 1, you will see that this is going to give you a saddle point. Now, when you draw this figure, and if I draw like this, do not label this axis, because now this point is your 1 1, that is the equilibrium point, not the origin. So, I will not give the exact position of the axis. So, what does this mean? So, I will write that this is not the 0 0, I will just write 1 1, and since it is a saddle point, then I draw these two lines like this. It is moving away, and you draw your curves. So, it is wise that you do not level your figure, you just get the dynamics and you write what kind of dynamics you are getting. So, we end our lecture today, and in our next lecture we will be taking this to the next level, where I will explain that why when the two eigenvalues are positive, why you are getting that as a node, why not it is a focus. Till then, bye bye.